Hello, everybody. Just give it a few minutes for people to file in. In the meantime, I'm always curious to see who kind of shows up to these things. So if you want to post, like, honestly, where you're from or what industry you work in, that would be really cool to see. But no worries. Start in maybe a minute or two. Okay. Great. I think we can at least start moving through. Hello and welcome to our talk about using ClickHouse for observability. To get some housekeeping items out of the way, please put your questions in chat. We'll go over them as they come up, and any that get missed we'll cover at the end. This is being recorded. We'll send you a copy to review after it's over, along with some links to useful stuff, including like demo scripts and things like that. And then throughout the talk, we'll have some poll questions for you all. And the first one is just to kind of gauge everyone's experience with ClickHouse. Now to the agenda. We'll start by looking at what ClickHouse is, what features that it has that makes it stand out from other databases. Then we'll go into the architecture that enables those features and how ClickHouse works under the hood. Next, we'll wrap all this info up into use cases and observability, and specifically look at how we use ClickHouse at Aiven as part of our backend management plane. And then lastly, we'll have a demo so you can see all this in action, and then try it yourselves later on. This is us. I'm Ryan from the solution architecture team here in North America. I'm based in Boston, and I'm joined by Ville, who's also on the solution architecture team in EMEA. So what is ClickHouse? Shortly put, it's a really fast analytics database. But I've seen a lot of people, myself included, try to apply knowledge they have about how other databases work to ClickHouse, or just move workloads from other databases directly to ClickHouse as is and expect performance gains. And don't get me wrong, that can happen, but you can also mess things up in the medium to long term if you aren't familiar with some of the ClickHouse's quirks. So we'll kind of start from the beginning. And if I was going to build a high performance analytics database from scratch, what would I be doing to optimize my speed? And if you look at the main reasons databases are slow, they kind of boil down to three things. You have too much disk I/O, which is relatively slow and expensive. You have different processes that are blocking each other. And then you have resources that are not properly allocated and utilized. So if I were going to create a database to solve these problems, I would want to address these 3 points, and we'll see how ClickHouse addresses them. So first of all, we want to read as little as possible. And for an analytics database, that probably means it needs to be columnar storage. Most databases store all the data in a table in a heap in which each row is stored together, one after another. And this works very well for online transaction processing database, or OLTP. These databases generally act on a few rows at a time, so having all of the rows stored together where it's easy to access makes sense. You only need to read the chunk that the row's in from the disk into your cache. So far, so good. But analytics workloads are different, also known as online analytics processing, or OLAP. These will often look at the entire table in aggregate, but maybe only a few columns. But based on how it's stored on disk with a standard row story, you'd need to read every single row and every single column. So column or column store databases are the opposite. All the data for each column is stored together, and rows aren't stored together at all. This makes it really quickly to read all the values for a single column, maybe something like just the amounts number in a transaction table, to get revenue for the year. Additionally, since the data in the same column is more likely to be similar to each other, or compared to like all the different data in a row, the columns generally compress really well. And ClickHouse in particular allows you to use a variety of encodings based on your knowledge of the data to get maximum efficiency in your storage. And indexes are a pretty common solution to the problem of read as little as possible. You sacrifice some storage and time during inserts to take notes on where your data is, and then during those queries, you can use those notes to find data faster, which allows you to read less. ClickHouse has two index types, primary and skipping. The primary index is the data the order is written in the file, similar to like a clustered index, but each file has its own. And then since you as the administrator can define this, you can tailor it to your common query patterns or filters. If you always query for a certain time range, you can make sure that that's one of the first columns. So your data is ordered by time and the data you need will be stored together. Maybe you're storing logs and want to always include the source, like a particular app or service. And then if the primary index includes that column, your data will be easier to find and you don't need to read the whole table. Skipping indexes are stored alongside the table and refer to a specific column that you need. The purpose of this is to allow you to skip certain sections of the table because you know there's no data you're looking for in those sections. And there are a few different kinds that work well for different data types. And then I'll go into more details on both of these in the next section. Now, while transactions are critical for many standard database workloads, the ability to say, don't do any of this unless you can do all of it, is basically required for ensuring that your data is consistent and reliable, especially in OLTP databases. But all the architecture that enables that can be a downside in large-scale analytics. You don't want to block queries while you load data, especially real-time streaming data, which is constantly happening. And you don't want your queries to block your ingestion process because that slows things down, can cause backlogs, and just break all kinds of stuff. And yes, you can do things like read committed snapshot isolation, but these add overhead. So ClickHouse just says, speed is more important than ACID compliance. There aren't transactions, nothing blocks anything else. And there's less concern about inconsistent data because queries are still run against the parts that exist when they begin, similar to how read committed snapshot isolation works, but lighter weight. And two, you aren't doing the same sort of multi-step updates and queries you do in more transactional databases. The other part of consideration is that there's always a tension between the advantages of batch data or streaming or real-time data. With real-time data, you get the latest and greatest and can use it to quickly make decisions. Batches are generally slower as the updates happen less frequently, and you sometimes will need to wait for fresh data. But there are advantages to batching. You get better compression, fewer smaller files to manage if you write everything into big chunks. ClickHouse's architecture gives the best of both worlds. Fresh data can be written constantly as fast as possible, and then an automated process compacts it in the background, reducing the number of files, compressing the data, and keeping the cluster healthy and optimized. And then not requiring transaction supports also makes it easier to scale up as well as out. There's no need for a single coordinator to ensure consistency, which enables you to scale up to hundreds of nodes in a cluster, each of which can be read from or written to. You can either scale horizontally by adding replicas, which are extra copies of the data, either for high availability or more read throughput, or you can add new shards, which splits a data set into segments to efficiently scale your writes. And then queries can be parallelized and distributed across the cluster for efficient use of resources, no matter how big it is. The query engine is also optimized for high scale. Unlike an engine like Postgres, where each operator in the query processor handles one row at a time during execution, ClickHouse operators run on small batches, and then each core is given a disjoint part of the data set to work on at a time, enabling maximum use of compute resources. To tie that all together, this is how people describe ClickHouse. It's a relational database. It has tables, it has rows, it has columns. You can query it using SQL, which makes it accessible. It stores data by columns to optimize for analytical workloads, also called OLAP, and it's built from the ground up to provide high performance at scale with real-time data. So, how does the architecture work to achieve those goals? This is where we move from theory into implementation details, and we need to cover some terminology first. Tables are, as usual, rows and columns. ClickHouse does have a variety of table engines, though, which define how the data is stored. The most common is the merge tree, which also has some neat subtypes. And then there are the usual variety of external types like S3 or Kafka tables. Merge trees are what I'm going to focus on here, though. Your tables can be divided into partitions, which are actually implemented as folders on the file system. You define what partition scheme you want, and these serve a dual purpose. If you're filtering to certain partitions, you get partition elimination, which is nice for reducing reads. Additionally, it keeps it easy to remove old data, dropping whole partitions as they pass their time to live instead of having to rewrite the files to remove expired rows. Parts, and I do wish they had chosen a different name here because it's very confusing when you're new to have both partitions and parts, but they're the individual files which contain some amount of data. They can vary in size because of the merge process I described earlier. Initially, a part file is created whenever data is written to ClickHouse in one insert, and over time, those files are merged into increasingly large part files. And then lastly, a granule is the smallest amount of data you can read or index. And by default, it's 8,192 rows. Whenever you read any data, you read at least one granule. The primary index contains one entry per granule. Skipping indexes usually have entries that cover one or more granules at a time, defined when you create the index. This is very important for index design in ClickHouse, and it's kind of divergent from most other relational databases, which have index that can identify individual rows instead of just these chunks of 8,000 rows. Because the primary indexes are sparse, this also allows them to be stored in memory permanently, even at massive scale, to keep up high performance. Lastly, there are a few types of skipping indexes, which allow you to skip over granules that do not contain the data you're looking for. Min-max is what it sounds like. It stores the min and the max value of each block of granules for the column that it's defined on. This works really well when the data is loosely sorted. Set indexes store a list of all values for that column in the block. They work very well for data that's clumped together, so most rows in the granule have the same value, but different granules likely have different values. Text indexes are inverted index and store data as a list of tokens as keys and a list of granules which contain those tokens as values. So this is very similar to something like Elastic or OpenSearch, how they work to store data. And then Bloom filters are pretty cool. They predate text or inverted indexes, but what they do is they allow you to optimize the index size by allowing the possibility for false positives, taking a somewhat probabilistic approach. For example, a Bloom filter will guaranteed tell you which granule contains a certain value and then have a configurable chance that that value is not actually in the granule and you read it unnecessarily, but you definitely get everything that does have that value. And so this is how you can pretty efficiently index arrays or maps or even long texts using the token or n-gram types of Bloom filters. And then when you synchronously insert data, ClickHouse creates a new part file and stores the data in that file. That's it. No coordination, no latchings, no rewriting existing data yet. You can also set inserts to be async, which will allow ClickHouse to create a hidden buffer that will wait until a certain amount of time has passed or data has been written before writing out the part file. And this can be useful if you don't have the ability to micro batch your data very effectively in your upstream systems. And so you can kind of let ClickHouse handle it. And then after the file is written, it's copied to the other replicas for high availability. So far, so good. We're optimizing for write speeds in our real-time data warehouse. We expect data to be coming in constantly. And this is where the merge tree table engine comes in. In the background, it will merge these small files together, resorting, reindexing, reducing the total number of files to keep track of. Because remember, each part file has its own primary index, which is stored in memory. You really don't want to have too many of these like tiny files sitting around. You want them to be combined into more larger, efficient files. And one thing to be aware of is that since each partition is a folder, part files from different folders won't be merged. So you want to avoid having very granular partition structure, because that will limit the amount of merging you can do, and having too many part files can cause issues for the cluster. I mentioned that the merge table has some subtypes. There's a list here. They allow you to define further rules for what happens during merges. Rows with the same primary key can even be combined into a single row for efficient storage. For example, a summing merge tree will add together any non-primary key numeric columns when combining one or more rows. So you can kind of like sum things up over time if you don't need to keep the granularity of the individual rows. And then our next question for you all is, what is your existing observability stack based on too? So if you've been paying attention, you kind of already know how ClickHouse would fit into an observability stack. They kind of fit ClickHouse perfectly. Logs are being constantly generated and need to be ingested and available as soon as possible. And generally, you're only looking at certain fields. Your filters and query patterns will be predictable, often something like source or date or severity. You may have aggregations over long periods of time to analyze trends. ACID transaction requirements are not particularly important. And lastly, all your apps generate a ton of log data at big volume. ClickHouse seems like an ideal choice. So it was for us. Last year, we moved all the logs generated by our service from Elastic OpenSearch over to ClickHouse, and we were able to extend our retention period while saving money because of ClickHouse's both excellent compression and tiered storage. We currently run 2 3-node clusters to handle the system logs from our hundreds of thousands of nodes across all services used by all customers, and we store the last year's worth of data. Our architecture, our logs flow from the service nodes into Kafka. We do some minor transformations and batching in Vector, and then we write it all to ClickHouse. And then we have a mix of SQL query tools and Grafana dashboards to kind of keep an eye on everything. This is a sample schema of ours. We have a big table called messages. You can see all the things we've talked about being implemented here. We're compressing our columns using ZSTD with a compression level of 1. We have 2 very high impact indexes that are in our message column. This is a little bit behind the times, actually. Inverted indexes were recently built into text indexes with the name and the options changed, but they still work the same way. We use a replicated merge tree naturally. We partition by date. Nice and easy. Our primary key is timestamp our service ID and then timestamp. This, for us, effectively balances how we want to query our data. Sometimes we want to look at our entire state and notice systemic or repeated issues. So everything within an hour is grouped together. But often we're looking at a specific service and we want to, have all the details for that specific service all together. And then lastly, we keep the last 3 months on local disk. Everything older is moved out to remote storage. In our case, is a GCS. And then while Vile gets our demo set up, we have one more question for you. Also, I have a open question, which actually I guess I'll get to at the end. So let me stop sharing. All right.
So in today's demo, we'll be going through setting up a very simple observability pipeline using OpenTelemetry, ClickHouse, and Grafana. Now, after the talk, you're already familiar with ClickHouse, but we can just go through briefly what are OpenTelemetry and Grafana. So if we first start with OpenTelemetry, it is an open source project and a set of tools, APIs, and SDKs that help you collect and export telemetry data like logs, metrics, and traces from your applications and infrastructure. And today we'll be using the OpenTelemetry collector to collect our example logs and ship them directly into ClickHouse. And Grafana we'll be using as a visualization tool, essentially to view our logs, search through them, and explore the details. And here on the screen, you can see the Aiven console where we already have a ClickHouse and a Grafana up and running. But if you're not familiar with Aiven, I can briefly explain what is it. So Aiven is a platform that takes open source data technologies and offers them as managed services across multiple public clouds. So in a nutshell, you can select the type of technology that you want to use. You can select whether you want to deploy it in AWS, Google, Azure, whatever you're using in your applications. You can select the region and select the plan that is most suitable for your workloads. Once you click Create Service, Aiven will spin up the cluster, handle all of the management for you, backups, self-healing, take care of it essentially, so that you can just take the connection credentials and start working on your application so that you don't need to worry about the data infrastructure. Aiven also offers multiple integrations into external systems. It's possible to do private networking easily, and there's just a loads of different types of features for you to use. But now we can go into our existing ClickHouse, which is up and running. So you can see that in the Aiven console, I will get the connection information to it. I can see the metrics. I can see all the backups that I have, and it is deployed in Amazon Web Services EU North 1 region. And in addition to the Aiven console, Aiven also provides a Terraform provider, which I actually use to spin up these services so that I can control them programmatically. And I have a quick example here of what it looks like to run the Terraform file for this setup. So essentially, I'm just using the Aiven Terraform provider. I'm giving my API token to it so that it can connect on behalf of me. And then I'm defining my organization, my project where I'm deploying the services. And then I have my ClickHouse instance and my Grafana instances here, both of them deployed to the AWS EU North 1 region, ClickHouse having the startup 16 plan, and Grafana having the startup 1 plan. And then lastly, in the end, I am simply exporting Terraform output, which builds the URL that we need to connect into ClickHouse so that we can use it as an environment variable for our OpenTelemetry collector configuration. So I have these files here locally. I can go to the Terraform folder where you can see the Terraform file that we just viewed. And essentially, I've already run this because the service is up and running just to save time for this demo. So we can see that we have the output already defined. It's marked here sensitive because it contains our password in order to access the ClickHouse server. So what we want to do now is we want to just export it into an environment variable, something like hopefully no typos. And now we have basically from the Terraform side, everything ready. So in this example folder, we have a different directory also called OTel. And this directory contains everything that is needed for our OpenTelemetry connector. First, you can see that there is a file called access structured log. So this is our example data that we're going to be using this demo. If we quickly see what do we have here. It is essentially structured log data that is containing API requests, and there's about 10 million rows of it. Then if we go and see what is the OpenTelemetry collector about. So the OpenTelemetry collector is a tool that you can use to ingest the logs. You can process it, and then you can ship it off to your destination. The collector can be used in two different manners. You can use it as what we call an agent, or then in the gateway mode. In the agent mode, you have individual OpenTelemetry collector instances deployed alongside each of your applications. So basically on every server that you're running, they will individually collect the logs, process them, and then send them to the end destination. The other format that you can use is something called gateway, where you have one centralized OpenTelemetry collector, which is getting data from multiple agents across your fleet, and then doing all the processing in a centralized manner so that it's more efficient. And if you want to do changes to the processing, you don't need to do deployments to all of your nodes out there in the wild. And now in this demo, we are essentially doing the agent model. So we are reading our example logs files and sending them directly to ClickHouse. And if you look at the configuration file, what is needed for OpenTelemetry connector, we need to define 3 different sections. We have the receivers, how are we getting the data in? We have the processors, what are we going to do to the data? And then we have the exporters, where are we going to put the data? On the receiver side, it's quite simple. So we have a file log resource, which includes the example file that we just looked at. So essentially, it's just reading the file from disk. It will start from the beginning and parse it as JSON. So that's all that we need to define for our demo. We have another resource here, which essentially exposes an endpoint where you could, in your applications, use the OpenTelemetry SDKs to send out your logs to this easily. In this demo, we will not be doing this. We'll be focusing on the example file that we have at hand. But this is essentially how you can configure the collector. After that, we will process the data. So we have very simple processing. We're just going to be batching it. We're setting a timeout of 5 seconds and then a batch size of 5,000 for it. And then lastly, we're going to be sending the data into ClickHouse. So here we define an endpoint. You can see that we are using the environment variable that we just put in the previous part. And then we are giving some options to ClickHouse. The main option that you need to be aware of is this part. It's enabling async inserts. So what Ryan mentioned previously is that whenever you write a batch of rows into ClickHouse, it will first create something called the initial part file. So only those files are created into a part, and then later on ClickHouse will be merging them as it optimizes the data. But this means that if you write really small batches, like 1 row at a time, ClickHouse will create way too many files that it needs to be then handling later on. So what this async inserts does is that it creates a small buffer on server side on the ClickHouse so that it will ingest rows from different applications, put them into buffer, and then flush it once it's ready. So this will reduce the amount of initial part files that are created. And overall, this is a very important topic because batching is really important in ClickHouse. Typically, it's recommended that your batch sizes are something from 10,000 up to 1 million, because this is where ClickHouse is performing in the most optimal manner. Having too many small parts will cause you errors and an extensive CPU usage in your ClickHouse instance. So that's why batching is important. And in a large scale, you could probably use something like what Aiven does, where we put Kafka in front of ClickHouse, which naturally handles some of the batching aspects for you. After that, we just define the table name for the logs. So it's called OTel logs. And then we even have a flag for creating the schema. So the OpenTelemetry ClickHouse exporter already comes in with the functionality for creating the ClickHouse schema for you. So this is very simple to get up and running with. Then we just define the timeout, database name, we're using default, and a few other not that important things. In the end, we have just our service definition. So we say that we have the logs pipeline where we want to receive the data from the file, we want to process it, do some batching on it, and just send them over to ClickHouse. This is all you need to do to have a working setup. So if we start actually sending this data, you can see that I'm actually already also connected to our ClickHouse instance. We don't have any tables. If we start sending our data, now we run the same thing again. We can see that we have a table created for us. If we start running a count from that table, we can see it has 2.45 million rows now. We're ingesting with quite high speed, 3.3, 3.85. Okay, so our data is coming in all the time. And meanwhile, we're ingesting the data. We can just have a look at what is the schema actually looking like. So this is the schema that OpenTelemetry connector creates for us by default. And you can see that there's quite many similarities to what Ryan showed on what Aiven has been building on our own. So essentially, we have a bunch of columns like timestamp, trace ID, span ID, actual body where the log message is, service name. So if you have different applications and so on, we give them the appropriate data types like date time. We define compression algorithms for them so that it's most efficient. We have some other data types like low cardinality. So if we know that there's a limited amount of values, different values for this column, we can set low cardinality for it so that ClickHouse is able to optimize it even further for reads. But this is what it offers out of the box. In addition, there are some data skipping indexes, like Ryan mentioned. For example, for the body, we have the token Bloom filter that helps us actually very nicely look over log messages because it gives you the kind of like the certain options, but also some potentially false positives. The schema that this exporter gives you out of box is good for getting started, but most likely, if and when you're running things in production, you want to modify it for your specific needs. But it's a good starting point, especially for testing. Then in the end, we have engine, which is a replicated merge tree engine. We are running at the moment a single instance of ClickHouse, so we could also use the merge tree engine directly without the replicated part. But Aiven does this automatically for you because in our platform, you can easily scale up from 1 node to 3 nodes. And so we just do it out of the box to make it easy for you. We partition the data by to date. Like Ryan mentioned, it's going to be easy to delete the parts. And also, that's a very common value to search in as well. Then we have primary keys. We have the service name, timestamp, order by, very similar to that. So yeah, all good. But one of the promises that ClickHouse had was also in its ability to compress data. So this is something that we can actually view right now. So if we check how much data do we have now? Okay, we're at the end of our example data. So we have 10.37 million rows in the table currently. But we can actually have a look at the size in more detail. So if we run something like readable size, bytes. Okay, here we are looking at the system parts table that contains internal structure of ClickHouse. We are going to be summing the amount of uncompressed bytes and compressed bytes so that we can have a comparison. So if you have a look at that, oh no, there's something wrong in my query. There we go. Yes. So if we have a look at the data, the uncompressed value that we have is 8.44 gigs, and the compressed value is 500 megs. So ClickHouse is extremely efficient, even in this case, when things are maybe even not fully optimized in compressing all of the data. And this allows you to have quite a bit of retention on local disk as well. So you don't need to delete your data too often, or then you can set a higher value for tiered storage as well. But all right, so we have now successfully added the data into ClickHouse, and we are ready to actually use it. So like I mentioned, for that, we're going to be using Grafana to visualize the data. So I have an instance of Grafana up and running at Aiven in the same region at the moment. And what we want to do is we want to connect it to the Aiven ClickHouse and then create a dashboard where we can search for logs. So what we first need to do is we need to add a data source. So we need to connect to the ClickHouse instance. For this, we need to give it the connection details from our service. We're going to be using the native protocol in order to do this. We want to add the host. We want to add the port. It is a secure connection. And then lastly, we just want to add the details for our user. Save and test. Yes, we have a working data source. And now we are ready to build a dashboard in Grafana. So we are adding a new panel. We can select the data source that we just added. In Grafana, we can modify the visualization to use, for example, the default logs panel that they have. In the query builder itself, it's very simple when you use this example dataset, because you can just select that I want to use logs, I want to use OTel, and you have your data. That's it. That's all that we need to do in order to get our logs visible on the screen. You can modify the panel, of course, to your kind of like needs. I personally like to use this time mode so that it shows the timestamp first, and then I can dig a bit deeper into the log message itself. So now I can just say, I can save my dashboard, say, let's maybe add logs dashboard. And we have it available for use for our users. Maybe make it a bit bigger so that it looks nicer. And the only thing that is missing, it really is search here. So what we want to do in Grafana, we want to add a variable, text box variable, so that the users can type their queries into it. Say log search, give it a label, search. And that's about it. If you go to the dashboard, yeah, you can see that we have a search here, and the only thing that we need to do is to actually connect it to our panel. So here in the query builder, there's already a field for message filter, and we just need to add our variable here. That should be good. If we go to our dashboard, say we want to search for post messages only, you can see that the data has changed according to our queries. So this is essentially how you can build an end-to-end log collection pipeline in a very short amount of time. Then the only thing that you kind of need to worry about is, okay, now with the default schema, we are ingesting data basically forever. So at some point you will run out of disk. On Aiven, you can of course extend your disk and have a bigger instance always. That's no problem, but typically you don't probably want to store all of that. So that's why you use the TTL statements that Ryan already showed you, so that you can define in ClickHouse when should your data get removed, or should it be moved to tiered storage, which is a fantastic feature of Aiven, where you can ship essentially older data into object storages like S3, which makes it really cost efficient to have a very long retention for your log. So you can actually go really good back in time and see and do proper like anomaly detection and so on. How does the tiered storage work? I can show you quickly just the steps that you need to do in order to enable it. So essentially, here you can see that we have our table, hotel logs, and the only thing that we need to do is first activate tiered storage. That is now done. So if we go back into our ClickHouse, the only thing that changed here basically is that there's a new setting automatically added, which is storage policy tiered. This means that it exposes the remote volume where we can start shipping our data. And if we actually want to move older data into tiered storage, the only thing that we need to do is we want to use this timestamp time column to determine when data should be moved. So the only thing that we need to run is alter table, hotel logs, modify TTL, where we want to say time. It's based on timestamp time plus interval, say 1 month to volume remote. And that's it. Now ClickHouse will in the background start moving data into object storage seamlessly. And from the client perspective, you can query your data just as usual. It doesn't know whether the data is coming from the local disk or is it coming from the object storage. ClickHouse will handle all of that for you in the background. Of course, when you need to fetch from the object storage, it comes with some added latency. So, which is why for the queries that you run most often, you want to still always have the data be on local disk. But that's it for the demo today. Hopefully that was helpful in getting the first hotel ClickHouse Grafana pipeline up and running.
Okay, great. Thank you. And so just to wrap up, I like ClickHouse. I think it's really cool, but it's definitely not a one-size-fits-all solution. It's purpose-built to do one thing really well. And there are some times when it will not be the right choice. Number one is big and bold because it's very important. Do not use ClickHouse if you need ACID compliance or transaction support. As you've seen, it's and then as you've seen, ClickHouse is not really optimized for updating a single row either, because it will have to rewrite these increasingly large part files every time. So kind of you want to avoid just standard updates and delete. Lastly, this is a little less true now. There's been a bunch of improvements around join performance, but still worth mentioning. It's not really intended to do a lot of like super complex joins. It's better to have very wide tables with lots of columns. And then have those columns contain all the information you want. And then lastly, we have a poll question from our product team that was about some questions or some things that they were considering. Lastly, if you want to try it out, I feel I showed it off earlier. We have a 30-day free trial on our Aiven platform. You can use the code specific to this workshop that comes with $400 in credits, and you can get started with no credit card, just an email. And then last, we'll do the QA, I think. If there's any other questions, feel free. But I typed out most of these answers already. But for the audio only enjoyers. So how is it determined in which granule a value is going to be written? This is a slightly backwards question because how data isn't really written to a specific granule. Data, when it's inserted, will be written to a part file, and then that part file is ordered by whatever the table order by clause is. And then that file is logically broken up into granules of 8,000-ish rows each. So which granule each row is in is determined by the order by key. But also it kind of doesn't matter aside from what else is in that granule and what your indexes and stuff are. And then question about replicated merge tree instead of merge trees that ended up being modified into a different question. But replicated merge trees add a small amount of latency to the time that is available, the data is available at. So your inserts still happen instantly because the replication is done asynchronously, and your queries are querying whatever data is available. So no latency there by using replicated merge tree instead of just merge tree. But the data that there will be a little bit of latency between when the data is written to whatever node it's written to and when it's available for query on the other nodes. And since the data is copied over after it's been like compressed and all that stuff, it's usually pretty quick. And this also means that you don't just have one copy of your data, you have multiple copies. So if you lose a server or lose a AZ or lose a data center or something like that, you still have your data. And then follow up for all the special merge trees like replacing, summing, all those type of merge trees. They are very interesting, but they do have a kind of important gotcha, which that you cannot assume that the data has been merged because it doesn't, because again, it kind of happens in the background on its own schedule. So you have to write your queries being okay, assuming that the data hasn't been merged. Again, depending on which table engine you're using, like the logic needs to be different, but usually it means doing some aggregations, doing some group buys, and writing your queries in a way that it will work whether the data has been merged or not, so that you don't have problems with that. Hello, I was expecting to see more APM capabilities instead of just log collection. How have you solved this? Create dashboards from scratch, or is there existing dashboard? We build most of our own dashboards from scratch, and a lot of our metrics is not in ClickHouse. Actually, we use Thanos for a lot of our backend metrics as a metric store. And then, we've built a lot of our monitoring tools and Grafana dashboards from scratch in-house. And this is kind of what one of those questions was leading towards is, would people be interested in hey, here's a fully managed, this is what Aiven does for logs and metrics as a product offering, instead of what we currently have, which is, hey, here's all the building blocks that we use and other people use, and you can kind of build your own stuff. I will say, though, if you are using Thanos as a backend metrics, we have a bunch of dashboards that come out of the box. So you say, okay, I have Aiven Kafka service or something. You write out the Kafka metrics to Thanos. You put a Grafana dashboard on top of that. If you do that all through the console, which you can do with just a couple of clicks, we have a bunch of pre-built dashboards for that. That's like, okay, here are the important metrics. Here's all the server metrics. Here's all the Kafka metrics that come right out of the box. And those mirror what we use internally to monitor the health of our services. Cool. Any other questions, topics, things people want to talk about? And obviously, thank you all for coming. I really appreciate it, and I hope you learned something and had a good time. Yeah, Q&A. That's it. Great. Well, everyone go get a coffee. We're leaving a little early today. Thanks.
Thank you very much.